Exponential decay has several different names depending on the real world situation. But mainly it's known as exponential decay. You could also hear it as depreciation or a half-life. With that, we'll talk about that in a little bit. I just want to talk about the basics of what is exponential decay. So exponential decay means that we're still in the form of y equals a times b to the power of x. A is still our initial amount. And b, instead of having a growth factor, this is our decay factor. In order for it to be an exponential decay, our graph is going to look something like this, where we have a high number and it's going to slowly and slowly, well, I shouldn't say slowly, it's going to decrease exponentially. Okay, so it's going to rapidly decrease and then it's going to kind of simmer down into a limit. So with that being said, our growth factor, our decay factor has to be a certain number. By certain number, the b value has to be between 0 and 1. So it's a fraction. We're cutting it in half. We're cutting it in thirds. We're making it smaller. That doesn't necessarily, a lot of people think when you think of exponential decay that it makes it negative. That's not the case. In order to make it decrease like that, you need to have a fraction. Okay. So here's my example. So a half-life is where a certain substance gets cut in half by a certain amount of time. Okay, so depending on whether you're talking about carbon-14 or if you're talking just about anything, it could vary in how long a half-life will take. But they will always give you a number so you have an idea of how long it's going to take for something to have a half-life. So, for example, the half-life of a certain radioactive substance is 40 days. If you start with 10 grams, write an exponential function. Okay, so looking at this, our A value is our initial amount, which is 10. Our B value, it's a half-life. So we're cutting everything in half. Our X value, so this is kind of like when we had our exponential growth equation. We have 40 days. So this means that the X is really divided by 40. And this represents 1 day. And the reason why is because we're dividing it by 40. So we can now write our exponential function. Our exponential function is going to be f of x equals 10 times a half to the power of x over 40. So if I were to ask you, okay, well, how many grams are left? After, oh, let's go with 60 days. So we can now enter this right in. because we've taken care of that half-life with 40, we take that 60 over 40 to tell us how many true half-lives that is. So we've got 10 to the power, 10 times 1/2 to the power of 3 over 2. So type this in because I can't do that in my head. 10 times 0.5 to the power of 1.5 gives us approximately 3.5 grams left. Okay, so even though it has that special term of half-life, that just tells us that the B value is 1 over 2. And we just need to figure out the X in terms of our half-life. So this is where we did the X divided by 40. That can change depending on whatever it is you're working with. Something to note, they will try to throw you off with negatives. And what I mean by that is if I were to have y equals 3 to the negative x, does this represent exponential decay? And they're trying to throw you off because of that negative. So what you actually need to do is have y equals 3 to the power of negative 1 to the power of x. So it's like what we've done before with exponents where we split the exponent. Well, 3 to the negative 1 gives us 1 over 3 to the power of x. This is actually exponential decay. Our initial value is 1. Our b, aka our exponential decay factor, is 1/3. So this does represent exponential decay. And that's something to note. They will try to throw you off with that negative. But if it were, say, y equals negative 3 to the power of x, you can't do anything with that. It's just a negative 3. That doesn't mean that you're decaying because it's not between 0 and 1. Okay, so this really gives you negative 1 is your initial amount, and then 3 to the power of x. So that would be different. So that's not actually exponential decay.